Hello, everybody. My name is Wang Teng. I come from Xi'an University of Post and Telecommunications. I'm very happy to present our recently work to you. The title of my presentation is Real-Time Stream Statistics with Local Differential Privacy in Mobile Crowdsensing. I will introduce our work from 5 perspectives. Firstly, I will introduce the background of our work. Mobile crowdsensing has greatly promoted and facilitated the big data collection, analysis, and utilization. However, the continual collection and analysis of stream data has seriously violated the privacy of each user and causes severe impacts because such stream data involve in individuals' identity, location, health status, or other sensitive information. What's worse, the privacy leaks will gradually accumulate as time continues to grow. Differential privacy as a rigorous privacy paradigm has been widely adopted to provide users with privacy protection in real-time monitoring. Local differential privacy is a distributed variant of DP. It's enabled to provide privacy guarantees for each user locally, and it's independent of any assumptions on servers, which can be used for privacy-preserving streams publishing. When considering the dynamics and correlations of stream data, the privacy-preserving mechanisms for real-time stream data processing is still in early stage of research. In nature, the privacy-preserving concerns of real-time statistics mainly cover twofold challenges when considering mobile crowdsensing. The first challenge is non-local privacy. Existing studies on real-time stream statistics mainly use centralized differential privacy that assumes a trusted server. But in mobile crowdsensing systems, the servers may be untrusted and interested in users' sensitive data. The second challenge is low data utility. The stream data are highly sparse and dynamic, and has complex time correlations. Therefore, if we directly use LDP privacy model, the direct perturbation on stream data is vulnerable to low data utility. Therefore, in this paper, to address these two challenges and further improve data utility, we propose a local differential privacy-based stream data collection and statistics mechanism, which incorporates a retroactive grouping strategy to get noise smoothing in an adaptive way. In summary, we make the following contributions. First, we propose to perturb stream data of each user on the client side by applying LDP, which will prevent privacy leakage from the data source when considering untrusted servers in crowdsensing. Based on the randomized response techniques, the local perturbation is performed on each user's stream data to achieve omega event epsilon LDP at each timestamp. Besides, we designed a retroactive grouping-based noise smoothing strategy to reduce noise error in stream aggregation and estimation. The retroactive grouping strategy can adaptively exploit the time correlation of the dynamic streams, that's making noise smoothing effective and improving data utility. Finally, we conduct extensive experiments on two real-world data sets. The results demonstrate that our mechanisms can improve data utility while ensure strong privacy protections. Next, I will present some preliminaries and our system model. Firstly, in this paper, we adopt local differential privacy as our privacy model. Because LDP is a distributed privacy model and has been extensively used by many applications and many data statistics tasks, such as mean estimation, such as machine learning, and so on. The definition of local differential privacy as shown in this page. And next, I will show you our system model. In our paper, we consider a large distributed mobile crowdsensing system that consists of abundant local sensor nodes. The sensor nodes can be mobile smart devices such as mobile phone, smart watch, smart glasses, and so on. And we assume that there is a central server. Each node randomly participates in a sensor task and uploads the sensor state to the central server in real time. The central server will aggregate the data stream and conduct statistics. We don't make any assumptions about the credibility of the server. That is, the central server can be honest or honest but curious. Next, I will show you our stream model. Since our system model is distributed, the stream model is also distributed. Each user hosts an infinite source stream dataset, and each tuple in dataset is an automatic record donating the user what in state S at time t. Based on the system model, each user's infinity stream data can be donated as xi. Based on the stream model and system model, our problem in this paper can be formalized as collecting the stream data of each user with omega event epsilon local differential privacy and estimating the stream statistics while guaranteeing a good data utility. Next, I will show you our main solution. The main design rationales of our solution incorporates two aspects. The first is local privacy protection. We apply the randomized response techniques to achieve local differential privacy for each user in the client side. And the second design rationale is time correlation exploration. We propose to learn the underlying time correlations of the stream under LDP, and then we can smooth the excessive noise to improve data utility. Based on these two considerations, we propose a local privacy-preserving mechanism for real-time stream statistics in mobile crowdsourcing. The overview of our solution is shown in this page. As we can see, our mechanism mainly consists of two components. The first is local participation on the client side, and the second is the aggregation and estimation with error reduction on the server side. The detail of each component will be introduced next. The first is local perturbation on the client side. Our perturbation rule is shown in this page, in which F determines the privacy level. And this algorithm shows our local perturbation algorithms. The specific due to the time space, I don't introduce the algorithm in detail. The second component is aggregation and estimation with error reduction on the server side. In this component, we designed a retroactive grouping strategy, which can reduce total noise and improve the data utility. The aim of retroactive grouping strategy is to divide the timestamps into groups based on the stream received so far, in which the grouping rule is that the stream data in the same group have a small deviation value from their average. In our paper, we adopt the deviation function to measure the deviation value. The deviation function is given in this page. This algorithm shows our stream aggregation and estimation procedure with error reduction on the server side. Finally, we have conduct extensive experiments to validate our solutions. We conduct extensive experiments on 2 real-world data sets, and we use the metric of average relative error to evaluate the data utility of our proposed mechanism. Inform the average relative error is defined in this page. This is our experiment results. This picture shows the average relative error of our mechanisms on 2 data sets when using noise smoothing or not. As we can see, the ARE under noise smoothing is always smaller than that without noise smoothing. This is because the noise smoothing can reduce the total noise based on the considerations of time correlation. Therefore, it demonstrates that the retroactive grouping strategy can learn the stream changing trends, that's making noise smoothing effective. Next, this paper shows the evaluation results of threshold selecting. As we can see, the adaptive threshold selection in our mechanism gives better accuracy in all cases than that using a fixed threshold. The reason here is that an adaptive threshold essentially reflects the changing trends of the dynamic stream data, which will make the time grouping more accurate, thus improving the data utility. Okay, our main solution has been introduced. I will make a conclusion of my presentation. In our paper, we propose a privacy-preserving mechanism with omega events epsilon LDP for real-time stream statistics in mobile crowdsensing. We leverage a retroactive grouping strategy to learn the time correlations and then smooth the excessive noise. Therefore, our solutions can guarantee a high data utility when publishing streams in real time. Okay, that's all. Thanks.